series on digital image processing. For last few classes, we were discussing about the image transformations. So, we have talked about the unitary transformation, we have talked about the Fourier transformation, and in the last class, we have talked about the discrete cosine transform. We have seen the discrete Walsh transform, discrete Hadamard transform. We have seen their properties and we have compared the performance of these transformation operations. In today's lecture, we will talk about another transform operation which is fundamentally different from the transformations that we have discussed in last few classes. So, the transformation that we will discuss about today is called KL transformation. We will see what is the fundamental difference between KL transform and other transformations. We will see the properties of KL transform. We will see the applications of KL transform for data alignment and data compression operations, and we will also see the computation of KL transform for an image. Now, as we said that KL transform is fundamentally different from other transformations. So, before we start discussion on KL transform, let us see what is the difference. The basic differences in all the previous transformations that we have discussed, that is whether it is the Fourier transformation or discrete cosine transformation or Walsh transformation or Hadamard transformation, in all these cases the transformation kernel, whether it is forward transformation kernel or inverse transformation kernel, they are fixed. So, for example, in case of discrete Fourier transformation or DFT, we have seen that the transformation kernel is given by Gxu is equal to e to the power minus j 2 pi by n into ux. Similarly, for the discrete cosine transformation as well as for other transformations like Walsh transform or Hadamard transform. In all those cases, the transformation kernels are fixed. The values of the transformation kernel depend upon the locations x and the location u. The kernels are independent of the data over which the transformation has to be performed. But unlike these transformations, in case of KL transformation, the transformation kernel is actually derived from the data. So, in case of KL transform, it actually operates on the basis of statistical properties of vectored representation of the data. So, let us see how these transformations are actually obtained. So, to go for KL transformation, our requirement is the data has to be represented in the form of vectors. So, let us assume a population of vectors say x which are given like this. So, we consider a vector population x which is given by say x1, x2, x3 say up to xn. So, these vectors x are actually vectors of dimension n. Now, given such a set of vectors or population of vectors x, we can find out the mean vector given by mu x, which is nothing but the expectation value of this vector population x. And similarly, we can also find out the covariance matrix Cx, which is given by the expectation value of x minus the mean vector mu x into x minus mu x transpose. So, here you find that x, since x is of dimension n, this particular covariance matrix will be of dimension n by n. So, this is the dimensionality of the covariance matrix Cx, and obviously, the dimensionality of the mean vector mu x will be equal to n. Now, in this covariance matrix, C x, you find that an element C I, that is an element in the ith row and ith column, is nothing but the variance of the element x I of the vectors x. Similarly, an element say C I j, this is nothing but the covariance of the elements x I and x j of the vectors x. And you find that this particular covariance matrix C x, it is real and symmetric. So, because this covariance matrix is real and symmetric, we can always find a set of n orthonormal eigenvectors. So, because this covariance matrix C x is real and symmetric, we can find out a set of orthonormal eigenvectors of this covariance matrix C x. Now, if we assume that suppose E I is an eigenvector of this covariance matrix C x, which corresponds to the eigenvalue lambda 1, lambda I. So, corresponding to the eigenvalue lambda I, we have the eigenvector say E I, and we assume that these eigenvalues are arranged in descending order of magnitude of the eigenvalues. That is, we assume that lambda j is greater than or equal to lambda j plus 1 for j varying from 1, 2 up to n minus 1. So, what we are taking? We are taking the eigenvalues of the covariance matrix C x, and we are taking the eigenvectors corresponding to every eigenvalue. So, corresponding to the eigenvalue lambda I, we have this eigenvector E I, and we also assume that these eigenvalues are arranged in descending order of magnitude. That is, lambda j is greater than or equal to lambda j plus 1 for j varying from 1 to n minus 1. Now, from this set of eigenvectors, we form a matrix say A. So, we form matrix A from this set of eigenvectors, and this matrix A is formed in such a way that the first row of matrix A is the eigenvector corresponding to the largest eigenvalue, and similarly the last row of this matrix A corresponds to the eigenvector is the eigenvector which corresponds to the smallest eigenvalue of the covariance matrix C x. Now, if we use such a matrix A to obtain the transform operations, then what we get is we get a transformation of the form say y equal to A into x minus mu x. So, using this matrix A which has been so formed, we form a transformation like y equal to A into x minus mu x, where you find that x is a vector and mu x is the mean vector. Now, this particular transformation, the transformed output y that you get, that follows certain important relationships. The first relationship, the important property is that the mean of these vectors y or mu y is equal to 0. So, these are the properties of the vector y that is obtained. So, the first property is the mean of y, mean of vectors y, mu y equal to 0. Similarly, the covariance matrix of y given by Cy, this is also obtained from Cx, the covariance matrix of x, and the transformation matrix that we have generated A. And the relationship between the covariance matrix of y is like this, that Cy is given by A Cx A transpose. Not only that, this covariance matrix Cy is a diagonal matrix whose elements along the main diagonal are the eigenvalues of Cx. So, this Cy will be of the form lambda 1 0 0. So, it continues like this 0, then 0, lambda 2 0, it continues like this, then finally, we have 0 0 0, and up to this we have lambda 1. So, this is the covariance matrix of y, that is Cy. And obviously, in this particular case, you find that the eigenvalues of Cy is same as the eigenvalues of Cx, which is nothing but lambda 1, lambda 2 up to lambda n, and it is also a fact that the eigenvectors of Cy will also be same as the eigenvector of Cx. And since in this case we find that the off diagonal elements are always 0, that means the elements of y vectors, they are uncorrelated. So, the property of the vectors y that we have got is the mean of the vectors equal to 0. We can obtain the covariance matrix Cy from the covariance matrix Cx and the transformation matrices A. The eigenvalues of Cy are same as the eigenvalues of Cx, and also as the off diagonal elements of Cy are equal to 0, that indicates that the elements of the vectors y, different elements of the vector y, are uncorrelated. Now, let us see what is the implication of this. To see the implication of these observations, let us come to the following figure. So, in this figure, we have a binary image, a two-dimensional binary image. Here we assume that all the pixel locations which are white, there an object is present, an object element is present, and wherever the pixel value is 0, there is no object element present. So, in this particular case, the object region consists of the pixels say 3 4, 4 3, 4 4, then 4 5, then 5 4, then 5 5, then 5 6 and 6 5. So, these are the pixel locations which contains the objects, and other pixel locations does not contain the object. Now, what we plan to do is, we will find out the KL transform of those pixel locations where an object is present. So, from this we have the population of eigenvectors, which is given by this. Just we consider the locations of the pixels where an object is present, that is the pixel is equal to white, and those locations are considered as vectors, and so the population of vectors x is given by, we have 3 4, because in location 3 4 we have an object present, we have 4 3, here also an object is present, we have 4 4, here also an object is present, we have 4 5, we have 5 4, then 5 5, then 5 6, and then 6 5. So, we have 1 2 3 4 5 6 7 8 vectors, 8 two-dimensional vectors in this particular population. Now, from these vectors it is quite easy to compute the mean vector mu x, and you can easily compute that mean vector mu x in this particular case will be nothing but 4.5. So, this is the mean vector that we have got. So, once we have the mean vector, now we can go for computing the covariance matrix, and you find that the covariance matrix C x was defined as the expectation value of x minus mu x into x minus mu x transpose. So, finding out x minus mu x into x minus mu x transpose for all the vectors x and taking the average of them gives us the expectation value of x minus mu x into x minus mu x transpose, which is nothing but the covariance matrix C x. So, here for the first vector x 1, we can find out x 1 minus mu x as, you find that x 1 is nothing but the vector 3 4. So, x 1 minus mu x will be equal to minus 1.5 and minus 0.5. So, we can find out x 1 minus mu x into x 1 minus mu x transpose. If we compute this, this will be a value equal to 0.25, 0.75, 0.75 and 2.25. So, similarly, we find out x minus mu x into x minus mu x transpose for all other vectors in the population x. And finally, average of all of them gives us the covariance matrix C x, and if you compute like this, you can easily obtain that covariance matrix C x will come out to be 0.75, 0.375, 0.375 and 0.75. So, this is the covariance matrix of the population of vectors x. Now, once we have this covariance matrix, to find out the KL transformation, we have to find out what are the eigenvalues of this covariance matrix. And to determine the eigenvalues of the covariance matrix, you all might be knowing that the operation is like this, that given the covariance matrix, we simply perform 0.75 minus lambda, 0.375, then 0.375, 0.75 minus lambda, and set this determinant is equal to 0, and then you solve for the values of lambda. So, if you do this, you find that this simply gives an equation of the form 0.75 minus lambda square is equal to 0.375 square. Now, if you solve this, the solution is very simple. The lambda comes out to be 0.75 plus minus 0.375, whereby we get lambda 1 is equal to 1.125 and lambda 2 comes out as 0.375. So, these are the two eigenvalues of the covariance matrix C x in this particular case. And once we have these eigenvalues, we have to find out what are the eigenvectors corresponding to these eigenvalues. And to find out the eigenvectors, you know that the relation is for the given matrix, for a given matrix say A, or in our particular case it is C x. So, let us take C x So, Cx into say vector z has to be equal to lambda times z if z is the eigenvector corresponding to the eigenvalue lambda. And if we solve this, we find that we get two different eigenvectors corresponding to two different lambdas. So, corresponding to lambda 1 is equal to 1.125, we have the corresponding eigenvector E1, which is given as 1 upon root 2 into 1 1. So, this will be the corresponding eigenvector. Similarly, corresponding to the eigenvalue lambda 2 equal to 0.375, this corresponds to the eigenvector E2, which is equal to 1 upon root 2 into 1 minus 1. So, you find that once we get these eigenvectors, we can formulate the corresponding transformation matrix. As we said, that we get the transformation matrix A from the eigenvectors of the covariance matrix Cx, where the rows of the transformation matrix A are the eigenvectors of Cx, such that the first row will correspond to the eigenvector, will be the eigenvector corresponding to the maximum eigenvalue, and the last row will be the eigenvector corresponding to the minimum eigenvalue. So, in this case, the transformation matrix A will be simply given by 1 upon root 2 to 1 1 1 minus 1. Now, what is the implication of this? So, you find that using this particular transformation matrix, if I apply the KL transformation, then the transformed output, the transformed vector will be y equal to A into x minus mu x. So, find that application of this particular transformation amounts to establishing a new coordinate system whose origin is at the centroid of the object pixels. So, this particular transformation, KL transformation, basically establishes a new coordinate system whose origin will be at the center of the object, and the axis of this new coordinate system will be parallel to the directions of the eigenvectors. So, by this what we mean is like this one. So, this was our original figure, where all the white pixels are the object pixels. Now, by application of this transformation, the scale transformation with transformation matrix A, we get two eigenvectors. The eigenvectors are this E1 and E2. So, you find that this E1 and E2, it forms a new coordinate system, and the origin of this coordinate system is located at the center of the object, and the axes are parallel to the directions of the vectors E1 and E2. And this figure also shows that this is basically a rotation transformation, and this rotation transformation aligns the data with eigenvectors. And because of this alignment, different elements of the vector y, they become uncorrelated. So, it is only because of this alignment the data becomes uncorrelated, and also because the eigenvalues of lambda I appear along the main diagonal of C y that we have seen earlier. This lambda I basically tells the variance of the component y I along the eigenvector E I, and later on we will see the application of this kind of transformation to align the objects along the eigenvectors, and this is very, very important for object recognition purpose. Now, let us see the other aspects of the KL transformation. So, this is one of the applications where we have said that this KL transformation basically aligns the data along the eigenvectors. Another important property of KL transformation deals with the reconstruction of the vector x from the vector y. So, by KL transformation what we have got is, we have got a set of vectors y from another set of vectors x using the transformation matrix A, where A was derived using the eigenvectors of the covariance matrix of x, that is Cx. So, our KL transformation expression was y equal to A into x minus mu x. Now, here you find that because this matrix A, the rows of this matrix A are the eigenvectors of the covariance matrix Cx. So, A consists of rows which are orthogonal vectors, and because rows of A are orthogonal vectors, so this simply says that inverse of A is nothing but A transpose. So, now inverse of A is very simple. If you simply take the transpose of the transform matrix A, you get the inverse of A. So, from the forward KL transform, we can very easily find out the inverse KL transform to reconstruct x from the transformed image or the transformed data y, and in this case the reconstruction expression is very simple. It is given by x equal to A transpose y plus mu x. This is a direct formation from the expression of forward transformation. Now, the important property of this particular expression is like this, that suppose here you find that this matrix A has been formed by using all the eigenvectors of the covariance matrix Cx. Now, suppose I choose that I will make a transformation matrix where I will not consider, I will not take all the eigenvectors of the covariance matrix Cx. Rather, I will consider say k number of eigenvectors, and using that k number of eigenvectors, I will make a transformation matrix say AK. So, this AK is formed using k number of eigenvectors, of matrix Cx. I am not considering all the eigenvectors of the matrix Cx. And obviously, because I am taking k number of eigenvectors, I will take those eigenvectors corresponding to k largest eigenvalues. So, obviously, this matrix AK, now it will have k number of rows and every row will have n number of elements. So, the matrix A will be of dimension k by n, and the inverse transformation will also be done in the similar manner. So, using this transformation matrix AK, now I apply the transformation. So, I get y equal to AK into x minus mu x. Now, because AK is of dimension k by n and x is of dimension n by 1, so naturally this transformation will generate vectors y which are of dimension k. Now, in earlier case, in our original formulation here, the transformation matrix y was the transformed vector y was of dimension n. But when I have made a reduced transformation matrix A considering only k number of eigenvectors, here I find that using the same transformation, now the transformed vectors y that I get, they are no longer of dimension n, but this y are vectors of dimension k. Now, using these vectors of reduced dimension, if I try to reconstruct x, obviously the reconstruction will not be perfect, but what I will get is an approximate value of x. So, let me write that expression like this. Here what I will get is, I will get an approximate x, sorry, I will get an approximate x, let me write it as x hat, which will be given by A k transpose y plus mu x. Now, here you find that the A k vector was of dimension k by n, vector y was of dimension k. Now, when I take A k transpose becomes of dimension n by k. Now, if I multiply this matrix A k transpose, which is of dimension n by k, by this vector y, which is of dimension k, obviously I get a vector which is of dimension n by 1. So, by this you find that this inverse transformation, it gives me the approximate reconstructed x, but the dimension of x hat, which is the approximation of x, is same as x, which is nothing but of dimension n. So, by this inverse transformation, I get back a vector x hat, which is of same dimension as x, but it is not the exact value of x, this is an approximate value of x. And it can be shown that the mean square error of this reconstruction, that is the mean square error between x and x hat, is given by an expression that EMS is given by sum of lambda j, where j varies from 1 to n, minus sum of lambda I, where I varies from 1 to k, which is nothing but sum of lambda j, where j varies from k plus 1 to n. So, you find that this mean square error, this term that we have got, you remember that while forming our transformation matrix A k, we have considered k number of eigenvectors of matrix C x, and these k number of eigenvectors correspond to the largest eigenvalues of matrix C x. And in this particular expression, the mean square error is given by the sum of those eigenvalues whose corresponding eigenvectors was not considered for formation of our transformation matrix A. And because the corresponding eigenvalues are the smallest eigenvalues, so this particular transformation and the corresponding inverse transformation ensures that the mean square error of the reconstructed signal, or the mean square error between x and x hat, will be minimum. That is because this summation consists of summation of only those eigenvalues which are having the minimum value. So, that is why the scale transform is often called an optimum transform, because it minimizes the error of reconstruction between x and x hat. Now, this is a very important property of KL transformation, which is useful for data compression. And in this particular case, let us see that how this particular property of KL transformation will help to reduce or to compress the image data. So, obviously, the first operation that you have to do is, if I want to apply this KL transformation over an image, I have to see how to apply this KL transform over an image. So, we have a digital image is a two-dimensional array of quantized intensity values. So, a digital image as it is represented by a two dimensional array of quantized intensity values. So, let us put a digital image in this form. Now, here let us assume that this image consists of n number of rows and n number of columns. So, there will be n number of columns and n number of rows. And as we have said that in order to be able to apply KL transformation, the data has to be represented by a collection of the vectors. So, this two dimensional image or two dimensional array, which consists of n number of rows and n number of columns, can be converted into a set of vectors in more than one ways. So, let us assume in this particular case that we represent every column of this two dimensional array as a vector. So, if we do that, then every column of this, so this will be represented by a vector say x 0, this column will be represented by a vector say x 1, this column will be represented by a vector say x 2, and this way we will have say n number of vectors as there are n number of columns. So, once we have this n number of vectors, for these n number of vectors we can find out the mean vector, which is mu x, and this is given by 1 upon capital N, then summation x I, where I varies from 0 to capital N minus 1. And similarly, we can also find out the covariance matrix of these n vectors, and the expression for the covariance matrix, as we have already seen, that this is 1 upon capital N summation x I minus mu x into x I minus mu x transpose, where this I will vary from 0 to capital N minus 1. And here you find that our mean vector mu x, this is of dimension capital N, whereas the covariance matrix C x, this is of dimension capital N by capital N. So, once we have obtained the mean vector mu x and the covariance matrix C x, we can find out the eigenvectors and eigenvalues of this covariance matrix C x. And as we have already seen that because this particular covariance matrix C x is of dimension capital N by capital N, there will be n number of eigenvalues lambda I, where this I varies from 0 to capital N minus 1, and corresponding to every eigenvalue lambda I, there will be an eigenvector E I. So, this E I, eigenvector E I here again will vary from 0 to capital N minus 1. Now, given this n number of eigenvectors for n number of eigenvalues, we can make the transformation matrix, we can form the transformation matrix A, and here this transformation matrix A will be formed as say E 0 transpose. I will write this as transpose because E 0 being eigenvector, and normally a vector is represented as a column vector. So, we will write the matrix A, which consists of a number of, where rows of this matrix A will be the eigenvectors of the covariance matrix A, covariance matrix Cx. So, this A will be E0 transpose, E1 transpose, and there are n number of eigenvectors. So, I will have E n minus 1 transpose, where this E0 corresponds to the eigenvalue lambda 0, and obviously, in this case, as we have already said, that our assumption is lambda 0 is greater than or equal to lambda 1, which is greater than or equal to lambda 2, and continued like this, it is greater than or equal to lambda n minus 1. So, this is how we form the transformation matrix A. Now, from this transformation matrix, we can make a truncated transformation matrix, where instead of using all the eigenvectors of the covariance matrix Cx, we consider only the first k number of eigenvectors, which corresponds to k number of eigenvalues, k number of the largest eigenvalues. So, we form the transformation matrix, the modified transformation matrix AK, using the first k number of eigenvectors. So, in our case, AK will be E0 transpose, E1 transpose, and likewise it will go up to Ek minus 1 transpose. And using this AK, we take the transformation of the different column vectors of the image, which we have represented by vector xi. So, for every xi, we get a transformed vector, say yi. So, here the transformation equation is yi is equal to Ak, this is the modified transformation matrix, into xi minus mu x, where this I varies from 0 to capital N minus 1. So, here you find that because AK is of dimension, the dimension of AK is k by n, and dimension of xi and mu x, both of them are of dimension n by 1. So, xi minus mu x, this is a vector of dimension capital N by 1. So, this particular vector, this is of dimension capital N by 1. So, you find that when I multiply this particular, when I perform this transformation AK into xi minus mu x, this actually leads to a transformed vector yi, where yi will be of dimension k by 1. So, this is the dimensionality of yi. That means, using this transformation with the transformation matrix AK, we are getting the transformed vector yi of dimension k. So, if this is done, if this transformation is carried out for all the column vectors of matrix of the two dimensional image, in that case I get n number of transformed vectors yi, where each of this transformed vector is a vector of dimension k. That means, the transformed image that I will get, the transformed image will consist of n number of column vectors, where every column is of dimension k. That means, the transformed image now will be of dimension k by n, having k number of rows and n number of columns. You remember that our original image was of dimension capital N by capital N. Now, using this transformed image, if I do the inverse transformation to get back the original image, as we said earlier that we do not get the perfectly reconstructed image, rather what we will get is an approximate image. So, this approximate image will be given by x I hat is equal to A k transpose y I plus mu x, where this x I hat here you find that it will be of dimension capital N. So, collection of all these x I hats, that gives you the reconstructed image from the transformed image. As we have said that the mean square error between the reconstructed image and the original image in this particular case will be minimum, because that is how we have formed the transformation matrix, and there we have said that the mean square error of the reconstructed vector from the original vector was summation of the eigenvalues which are left out, corresponding to which the eigenvectors were not considered for formation of the transformation matrix. So, here you find that because now in this case for getting the reconstructed image, what are the quantities that we have to save? Obviously, the first quantity that you have to save, the first information that you have to save is the transformation matrix A k. So, this A k needs to be saved. And the other information that you have to save is the transformed matrix or the set of transformed vectors y I for I equal to so the set of transformed vectors y I for I equal to 0 to capital N minus 1. So, if we save these two quantities A k and the set of transformed vectors y I, then from these two quantities we can reconstruct an approximate original image given by the vectors x I hat. So, you find that in this case the amount of compression that can be obtained depends upon what is the value of k, that is how many eigenvectors we really consider, we really take into account for formation of our transformation matrix A. So, the value of k can be 1, where we consider only one eigenvector to form our transformation matrix A. It can be 2, where we consider only 2 eigenvectors to form the transformation matrix A. And depending upon the number of the eigenvectors, the amount of compression that we can achieve will be varying. Now, let us see that what are the kind of results that we get with different values of k. So, here you find that we have shown some of the images. Here the top image, this is the original image. Now, when this original image is actually transformed and reconstructed using the transformation matrix with only one eigenvector. So, this is the eigenvector having which corresponds to the largest eigenvalue of the covariance matrix. Then the reconstructed image that we get is given by this result. So, here you find that the reconstructed image is not at all good, but still from the reconstructed image we can make out that what this image is about. Now, if we increase the number of eigenvectors in the transformation matrix, when I use 5 eigenvectors as the transformation matrix, then the reconstructed image is given by this one. You find that the amount of information which is contained in this particular image is quite improved, though this is not identical with the original image. If we increase the number of eigenvectors further, that is we use 25 eigenvectors to form the transformation matrix, then this is the reconstructed image that we get. Now, if you closely observe between these two images, compare these two images, you find that there are some artifacts. Say for example, in this particular region there is an artifact, something like a vertical line, which was not present in the original image, and that is improved to a larger extent in this particular image. So, again the image quality has been improved if I increase the number of eigenvectors from 5 to 35. Similarly, if I increase the number of eigenvectors further, if I go for 50 eigenvectors, the image is further improved. 100 eigenvectors, I get further improvement. If I use 128 number of eigenvectors, I get still a better reconstructed image. So, this way you will find that if I consider all the eigenvectors of the covariance matrix to form the transformation matrix, in that case the reconstruction will be a perfect reconstruction. So, here we have discussed about the KL transformation, where we have said the KL transformation is fundamentally different from the other transformations that we have discussed. So, earlier, that is the discrete Fourier transformation, discrete cosine transformation and so on, and there we have said that in those case of transformations, the transformation matrix or the transformation kernel is fixed, whereas in case of KL transformation you find that the transformation kernel, that is the transformation matrix A, which is derived from the covariance matrix, and this covariance matrix actually represents what is the statistical property of the vector representation of the data. So, here the kernel of transformation or the transformation matrix is dependent upon the data, it is not fixed. So, that is the fundamental difference between the other transformations with the KL transformation. But the advantage of the KL transformation that is quite obvious from the reconstructed images is that the energy compaction property, which we have said earlier, here in this particular case, in case of KL transformation, the energy compaction property is much higher than that of any other transformation. Here you find that the earlier result that we have shown, where using only one eigenvector as the transformation matrix, this particular result here, using only one eigenvector, still I can reconstruct the image and I can say what is the content of that image, though the reconstruction quality is very poor. So, that shows that the energy compaction in a eigenvector in the number of components is much higher in case of KL transform than in case of other transformation. But as it is quite obvious that the computational complexity for KL transformation is quite high compared to the other transformations, and in fact that is the reason that despite its strong property of energy compaction, KL transformation has not been much popular for data compression operations. With this, we come to the end of our discussion on transformations. Now, let us see the answers to our previous day's lecture. So, here it is quite obvious that property of the DCT which makes it popular for image compression applications is the energy compaction operation, energy compaction property. The transformation kernels for Walsh transform, Hadamard transform has already been discussed during our lecture. Significance of modified Hadamard transform. So, here we have said that by modified Hadamard transform, I mean the ordered Hadamard transform. The significance of ordered Hadamard transform is that here we can correlate the sequency of the signal with the variable u, which is done in case of DFT or in case of DCT, where the increasing value of u means increasing value of frequency components. And here equivalent to the frequency component in case of Hadamard transform, we have defined what is called sequency, and the increasing value of u should indicate increasing value of sequency, and that is basically the significance of this Hadamard transform. And we have seen during our last lecture that because of this, here also we can get some energy compaction property, that is most of the energy is confined within few Hadamard coefficients. The fifth problem, it was a problem where you have to find out the Walsh transformation coefficients of the following samples. This is also quite simple from the discussion that we had. If I simply replace these values in the Walsh transform expressions that we discussed, then we will get the Walsh transform coefficients. Now, coming to today's lecture, questions on today's lecture. The first question is, what is the fundamental difference between KL transform and discrete cosine transform? The second question, in what sense KL transform is optimal? Third question is, how do you generate the transformation kernel for KL transform? Fourth question, what is the role of KL transform in object recognition? Fifth one, why is it important to arrange the eigenvectors in a particular order to form the transform matrix? And the last question, why KL transform is not popular for data compression operation? Thank you.